Hi, my name is Marc. I'm talking about our paper optimizing preprocessing for maliciously secure MPC. So yeah, we heard a lot about a few talks about ML, and you can use pivot triples also for matrices and convolutions. We first begin here any details about how you actually do that, since all these other talks focus about other things. So here I first talk about just some basics about convolutions, because we are talking about these operations. Then it makes sense to also know how these convolutions are structured. So here I start with a visual example. On the left we have an image for which we want to compute a convolution. And on the middle we have a so-called filter or kernel. And to compute the convolution, you align the filter on top of the image. Then some pixels align, you multiply the align pixels from the image with the pixel from the filter. And then you sum all these up, you get one pixel of the output. You move over your filter to the next set of pixels in the image, and you do the same until you cover all the pixels of your image. Then you can even move out, add your image, and you can then, for example, in a lot of applications, you might need something as big, an output as big as the input. So overall, you then have something like as many multiplications as your kernel size for every output. And also because matrix multiplication is very related, a lot of relation work applies matrix multiplication to do the convolution. So I also have here an example, still the same, but now we do it with the matrix multiplication. For that, we start again with binding these image and filter, and now we put all the pixels of the filter in a vector and all these aligned pixels of the image in the filter and in one row vector. We do dot product, and then we have one pixel output. Then we move over our filter again, and then we construct a second row for our matrix. So we just do this for all the locations of the output pixel. We get the large matrix. We do one matrix vector product and get the convolution here. And we just continue that for all the pixels, and then we can do one matrix multiplication for the convolution. But here in the matrix we have some redundancy because you have the same image entries just somewhere else in the matrix for that to work out. And now I'm talking about how to do that in MPC. So first, again, like the basic setting here, this is now maliciously secure MPC. So we have parties that want to compute a function. In this case, it makes sense to talk about ML use cases. For example, some parties have some data, some have normal weights. We're maliciously secure, so the adversary cannot only observe messages over the network or at some of the corrupted parties, but can also influence what the corrupted parties do. And we want that the result is either correct or the other way board, and the inputs of the honest party should stay as secret as we can catch with so only the output should be. And here our setting is also that all but one of the parties can be fully corrupted. In this setting, it's the speed protocol is very popular, so it's a quite efficient MPC protocol for arithmetic circuits based on secret sharing. So here, sharing picture slides echo practice for shares. They in this full threshold setting, they just sum off to a secret, and we can do all the linear operations without interaction. And in speeds, you use max on the shares, basically max on the share value. So you have a Mackie alpha, and every party has a share, and a share of the Mac value, so alpha, a share of alpha times x. And with these, you can still do the linear operations without interaction. And then for operations like matrix multiplication and convolutions, we use still beaver triples, but now the correlated randomness is not just like a one beaver triple for scalar multiplication, but a more complicated correlated randomness. And the correlated randomness is also not just represent chairs, but we have to have already properly authenticated chairs from login. So, yeah, not a share of A, B, and C, but also authenticated versions. And with beaver triples, you have your goal is to multiply two shared values, and you want to do this only with linear operations because that's all you can do on the shares basically easily. And for that you use the correlated randomness authenticated triple APC, where A and B are uniformly random and C is the product. Then you compute X minus A minus B, you basically have that information theoretically is your mask. You can open that without risking privacy. And then you do the beaver multiplication just with linear operations, and you do some things cancel out, and you get extra product. And you can do the same just for matrix multiplication, so basically all the lowercase letters change to uppercase letters, and you do now matrix multiplication. That's it. And also the same for convolution. Just change operation, and it basically works for any bilinear operation. There is also related randomness for operations where you don't have two operands, but just one operand. If you want to, for example, square something, or do like vector times the transpose of the same vector, then you can just do the same. You save a bit because you don't need a full triple, you just need a pair. And also the operation and opening things just come a bit cheaper because there's less stuff wrong than if you do it with full triples. That's also more complicated randomness where you have full triples. Here in this example, you basically have all the combinations of exponents, and then you can basically compute a polynomial with this more complicated chair. It doesn't make too much sense for big operations because it gets exponentially expensive, but this technique is used, for example, to do like 3 multiplications at once or something. And why do you care about these specialized triples in the first place? So here's an example if you would do like all the convolutions in resonance 50 with this normal scalar beaver triples. You are somewhere almost 60 gigabytes of commutations. If you do it with matrix triples, you're like 4 gigabytes, and convolution triples like 200. So you gain a lot by not doing these individual multiplications with the beaver triple, and also this redundancy in the matrix that I said at the beginning you avoid if you do the convolution start. And here's some numbers for the runtime. Here in this example, it's not as big as a computation overhead, but it depends on your limitations in the setting, but it can be still significant. So how do we generate these beaver triples in general? So one very basic and popular technique is just to use homomorphic encryption. So we have to do the multiplication or the matrix multiplication convolution in the offline way somehow before, and homomorphic encryption is a good candidate because you can multiply things without revealing the inputs to the other parts. So the standard approach would just one party has one of their random data, they encode it somehow to be able to encrypt it, and the other party does the same. With the other input, then they can, in a standard approach, use SIMD or homomorphic encryption with PGP or something like that. Then you get, here in this example, just some, but you can do other things too. Then you can decrypt the code and you get some or product or whatever your homomorphic encryption supports. Yeah, usually it's cheaper if not both of these operands are encrypted, so there are schemes that do it in this mixed way where you have a plain text suffix multiplication. Then we basically extend on the protocols in speeds that just do this all for scalar things to support any packing scheme that packs these vectors now in possibly multiple ciphertexts in a certain way, then does some operation on it, unpacks them, and you get something. So here in this example is again a convolution, but depending on how you pack and what operation you do on the ciphertext, you can basically do a lot of operations, matrix multiplication, convolutions, this special type of convolutions used in machine learning, 2D convolutions, depth-wise 2D convolutions as well. And we extend both standard techniques for speeds, one where you have the two encrypted operands and one where you have only one encrypted operand. So just to give an intuition how these packing schemes for convolutions might work, so the homomorphic encryption that you use in speeds is BGP, and there basically you work on polynomial rings. So your cipher-based multiplication gives you a polynomial multiplication. So if you just coefficient pack a vector data in the coefficients of a polynomial for two vectors that might look like this, to multiply them, we have like a shifted rotated version of the second operand. You align them where the coefficients overlap, you multiply them, sum them up. And then you rotate around the second operand until you're fully done with all the coefficients. And yeah, this looks very similar to a convolution, and it's in fact a negative side of convolutions, so everywhere it scraps around, you also multiply it by -1. But other than that, it's basically a convolution. So that not only works for these simple multi-convolutions, but also, like here is an example for the really more complex convolutions you would have to do in machine learning. So for example, we have multiple batches of images, each has different channels, and then your filters are also not just one filter, but you have like as many filters as your input channels times as many filters you want to have for output channels. So if you have 3 input channels and you want 2 output channels, then it's 6 filters. And here the output is as many batches as we input and as many output channels as we want. And each of the output channels is then the sum of multiple cross correlations, where the input channels match and the output channel matches the output channel you want to do. So, and how does the packing look here? For example, one way we can do that is you just write up all your filter and in the second ciphertext, and then write your image batch-wise where they don't overlap. And then if you do the multiplication, you will have again the same thing, that your filter wraps around. So if you pay attention, you see that also you save the filter and the channels in a different order than you actually want, because the multiplication turns it around again. And then when you do the one multiplication, what you get for output is some cross pairs that you don't really want, but then at specific indices, you get exactly what you want. You get a sum of multiple convolutions. And here, each of these blocks actually stands that for a full 2D image convolution, not just for a single pixel. Yeah, and if you just simply do that, at the end you just have to extract at the right positions and you get your result. Here's a comparison of what that brings you in the runtime. So to pre-process all these convolutions that I showed you before for the online phase, you need to generate them. If you would do it with fewer triples, or some prior work that uses more expensive homomorphic operations to do matrix multiplication, so they use cybertext rotations and cybertext multiplications, which is a lot of compute overhead. So we are 10 times faster than if you do it with the matrix approach. There we have the cheaper compute because we don't do the rotations, and we are more efficient because we don't go via matrices to do the convolutions. And so the baseline if you do scalar multiplications. It's like 30 times slower in the fast network setting. If you go to a slower network setting, then it's like 40 times slower, and the compute intense matrix multiplication also doesn't yet pay off. So if you would get much slower at some point, the homomorphic encryption from this related work would pay off. But yeah, it's like somewhat similar to compare HE and MPC. So another technique that's important for the maliciously secure MPC is sacrificing. So these base protocols that we use to generate the triples usually don't give us the correct triples, but just something like C is A times B with maybe some adversarial offset. So we have to check them again, because we don't want to use like two knowledge proofs to check that the multiplication was done correctly. So in the original speech protocol, you just generate two triples that are completely independent. Then you do the sacrificing step where you partially open one of the triples using some randomness, and then you do a check that this is 0. And if this is 0, you can use the first triple and you have to throw away the second triple. So that's just for checking that the relation holds. Then later in mascot that was improved where you have two correlated triples. So the B here is the same in the first and the second triple. So that's a bit cheaper to compute, and then also cheaper to check because you just have to open one thing. But you still the expensive part of the correlated triple is the multiplication, and you have still two multiplications here. And we also presented some way to avoid the sacrificing that Sebastian yesterday mentioned in his talk, where we extended that to the Z2K setting. So here we just if we have some building block that does the multiplication, where we assume that the parties have some equitable version of a share and locally another share, and they use that to get a share of the product, maybe with some offset, and then use zero hash proofs to give correct cybernetics to everyone. Then for the triple generation, both parties just sample their shares. They use this multiplication to authenticate B, so one part of it, and use encryption of the MAC key share. Then zero knowledge proof for A, and then what Sebastian already said, you just use one batch version of this multiplication protocol again to do the multiplication to get the triple part and to get the authentication for the whole rest of the triples, so for A and for A times B. And then if you later do the MAC check on this, these operations are chosen in a way. If you would cheat, then the MAC check. If you cheat with A, then the second MAC check would fail, and if you cheat with B, then the first MAC check would fail. So you can avoid the sacrificing and just do one MAC check in both that phase. Here is some results what that brings you now for that 128 by 128 matrix. So first line is again if you would do it with just normal Weaver triples. The second one is if we use our sacrificing avoiding technique to produce normal scalar Weaver triples. And then the same related work with the matrices. And then the last one is if we combine some matrix packing techniques to generate matrix tuples directly and avoid sacrificing. So avoiding sacrificing gives us like almost 2 times speed-up compared to the normal Eva triples, but yeah, still normal Eva triples are like 150 times overhead of directly doing the convolution and matrix multiplication. And yeah, here also we don't have these more expensive separates where you can do all the rotations. We just use plain text multiplications with the packing techniques, so we also save 60% overhead compared to the priority. And in the runtime, yeah, you see that here our work is much faster than the Eva triples and also the matrix-based approach that needs these separate exertations. And also for the slower network where you have, again, very high overhead for doing individual triples and still a factor 4 faster than the prior matrix approach. So overall, we have shown that we can more efficiently generate Eva triples in Maliciously secure offline base by avoiding sacrificing and using special techniques for packing matrices and convolutions. We first directly do the convolutions in a maliciously secure setting before it was all emulated with matrices, and we show that that gives you a more efficient online phase and a more efficient offline phase. We also have in a paper like depth-wise convolutions that were not included in prior work. And also we have for these pairs, like special protocols for generating matrix pairs. Like if you multiply a matrix by its own transpose set somewhere. Yeah, so I'm done.